Let's talk a little bit about the non-parametric options to one-way ANOVA. So when the assumptions are not matched from your experiment, you might need to use a non-parametric option. So for one-way ANOVA, this test is the Kruskal-Wallis test, and we'll just kind of take a quick look at it. So going back to the rat diet example, so our null hypothesis was diets F add the same means across the different diets. So the mean of the longevity within each of the diet groups was the same. That was our null hypothesis for a one-way ANOVA, for a parametric test. Now we're going to change that diets have the same distribution of longevity. So if this means that, so we're not saying that distribution is normal, just say they have the same shape of distribution. So including like things like the spread and the center, right? So if the distributions are the same, they should come from the same populations. So remember, non-parametric tests, they don't estimate means or spread measurements like variance or standard deviation. So the alternative for the non-parametric Kruskal-Wallis test would be that diets have different distributions of longevity. So in other words, if they have different distribution, they should come from different populations. So the formula, we're not going to derive this formula, but the statistic is this, for the Kruskal-Wallis test, is this H formula. So we have this number 12 divided by our total n, multiplied by n plus 1, and then we have a sum that includes this Ri is the rank. So remember, like most non-parametric tests use ranks, so the original values of the response are transformed into overall ranks across, in this case we had 5 rats per each of the treatments, so 15 total. So this will be a rank from 1 to 15, right? And then this sum is made for each level I from 1 to k, right? So there's a sum over the ranks for each of the groups. So you do this for one group, you do for the other group, and then for the other group, and then you multiply this fraction by this one. So if you just kind of run the numbers from, I'm not showing calculating the ranks here, but this whole formula would end up being H observed statistic of 7.6. So it has been shown that the Kruskal-Wallis H statistic is approximately chi-square distributed with degrees of freedom k minus 1. So k is the number of treatments. So here, remember, we have 3. So this is going to be the statistic that we should contrast our observed value would be a chi-square with 2 degrees of freedom for a given alpha, normally 5%. And this is going to be a one-sided chi-square distributed, which is kind of always like that. So if we do that, now I guess if the null hypothesis is true, this H, if you kind of think a little bit about the formula that I just showed in the previous slide, should be close to 0. If one or more groups has a mean rank that is different from the grand mean rank, then H will be a large positive number. In our case, we got 7.6. So, in other words, this statistic, this observed statistic, this H statistic is going to get larger and larger as you move away from the null hypothesis. So, if we looked up the chi-square statistic, critical value for this particular distribution, chi-square 2 degrees of freedom, we will find the value 0.10, and in our case we found an observed statistic of 7.6. This is much larger than that, so we will reject the null hypothesis. We could also get a p-value for this, and this actually ends up being 2%, 0.1. So notice that an important thing to notice is that normally non-parametric tests have less power than the parametric options. So I just copied here the p-value we'd observed for the one-way ANOVA for the same data. So less than 1%, and here we have 2%, right? So higher probability of observing this data under the null hypothesis of all treatment distributions are the same for non-parametric test. So less power here than here. So this is very typical for experiments with small sample size, which is the case for this rat experiment, and it's the case for many experiments in biology. and so higher power for the one-way ANOVA. When sample sizes are large, the power doesn't really change, so you'd expect to see similar p-values. So how to do this in R? So there's a readily available function, Kruskal.test, same type of formulation, response as a function of diet. So again, this formulation would only work if you attach the data frame like we've done for the ANOVA, because these are header names or names of the columns in a data frame, in a data set in R. Otherwise, you'd have to write the name of the data frame, which in our case was data $longevity. If you don't attach, you have to do this. If you close your session and you reopen, you lose the attachment, by the way, so you have to do attach data again. Anyways, the output is pretty straightforward. You get the observed statistic, the degrees of freedom, and the p-values. Pretty simple. So far we've talked about one-way ANOVA, what to do when we get a significant test, and then we've just seen non-parametric option. So non-parametric option, it's something that you take if ANOVA doesn't meet the assumptions. So here are kind of a little synthesis of the assumptions. So measurements are a random sample. This is both true for ANOVA and Kruskal-Wallis. The variable is normally distributed in each population. So this is an assumption for the ANOVA, but not for the Kruskal-Wallis. So it might be one reason to actually use Kruskal-Wallis instead of ANOVA. Although this had to be severely violated because ANOVAs and t-tests were robust to this deviation. By the way, Kruskal-Wallis is really just an extension of the Mann-Whitney U-test that we've seen as a non-parametric option for the two-sample t-test. And then the most important is that the variances are the same in all K populations ANOVA. This is just true for the ANOVA, and this is normally the reason why you go and use a Kruskal-Wallis, because you violate severely this assumption. So shapes of distribution must be the same in each population for the Kruskal-Wallis if you want to compare medians. So in the next lecture, we will be introducing two-way analysis of variance.